This is the second video on the 4 kinds of reactions, and here we're going to look at oxidation reduction. There are multiple types. We're going to start off with decomposition and synthesis oxidation reductions. And we're going to look at these 5 equations: the decomposition of calcium or any other kind of chlorite, the decomposition of water, decomposition of the salt potassium chloride, and then the synthesis of water from its elements, and the synthesis of calcium sulfide, a solid compound, from its elements. But we're going to generalize as well. So let's look at our first reaction, the reaction of barium carbonate being heated to form barium oxide, solid, and carbon dioxide gas. So let's review the type. This was on the the first of our videos. We identify the kinds of compounds that we're working with. Barium carbonate is an ionic salt. Barium oxide is an ionic oxide. Carbon dioxide is a molecular compound that comes off. If you look at the reactants and products, you see that the reactant here, the barium carbonate, and the barium oxide here with its carbon dioxide. The charge on the barium ion remains a 2+. Here in the barium oxide, here in the barium carbonate. So there's no oxidation or reduction going on. All we're doing here with the heating is making the carbon dioxide vibrate off from the barium oxide that it's taken charge of, and so you have barium oxide and carbon dioxide as the products. Carbonate decomposition, therefore, is a simple decomposition. There's no oxidation or reduction going on. If now you look at calcium chlorate decomposing to calcium chloride and oxygen gas, you immediately see, although you're getting a solid compound and a gas coming off, there is a difference. If we identify the kinds of compounds, calcium chlorate is an ionic salt. Calcium chloride is also an ionic salt. But oxygen gas is a molecular element. That's something we didn't see with the barium carbonate. Now look at the reactants and products as you see them here. The reactant, calcium chlorate, looks a great deal different from the solid product, calcium chloride, here on the right. And here goes oxygen as a gas and as an element coming off. The charge on the oxygen changes from a -2, implied from the fact that it's in that compound, to a 0 with the element. So the oxygen atoms have been oxidized from oxide to oxygen gas. Result: chlorate decomposition. All chlorates, when they decompose, that is an oxidation reduction reaction. Now, that can be sodium chlorate, calcium chlorate, potassium chlorate. All of them decompose in an oxidation reduction that forms oxygen gas. The same thing goes with bromates and iodates when they decompose. Now, let's look at the decomposition of liquid water. Let's see if we can discern the type of the above reaction. If we identify the species, we see that water is a molecular compound, but oxygen and hydrogen gases, the products, are molecular elements. If we look at the reactants and products, we see that the oxygen and hydrogen in water are bonded to each other, and we assign them charges of -2 and +1 respectively. But if you look on the right at the oxygen and hydrogen gases, you see elements with no charge, no bonds to anything except the very same element. Therefore, we have to say that water decomposition is an oxidation reduction reaction. Now let's look at the decomposition of a molten salt, in this case potassium chloride. This is how we get potassium metal, and you can get chlorine gas out of this to sell commercially. And let's determine the type of the reaction. We identify the species. KCl is an ionic compound. Chlorine, however, the product, one product, is a molecular element, and potassium is a metallic element. So we have to then conclude that potassium and chloride reactants are themselves ions, and they have assigned charges of +1 and -1 respectively. The chlorine gas has no charge at all. Potassium metals, like all elemental metals, that has no charge either. Therefore, we're seeing a movement of electrons, and that means potassium ion's been reduced to potassium metal, chloride ion has been oxidized to chlorine gas, and that means that all liquid salt decompositions like this are oxidation-reduction reactions. Now let's look at a couple of syntheses. Determine the type of this synthesis, where we burn hydrogen in oxygen gas to form liquid water. It'll probably be gaseous water until it cools down. Identifying the species, we can also see this is the reverse of the electrolysis of water we just looked at. Hydrogen and oxygen are elements with zero charge, and water, both the hydrogen and oxygen, are joined in a compound. Therefore, electrons have moved. Reactions with elements on one side and compounds of those elements on the other must involve a change of charge, and therefore movement of electrons. All syntheses of compounds from the elements, then, are oxidation-reduction reactions. This is another example. We can take calcium and combine it with sulfur. We have to do it at a higher temperature. And after the smoke clears, we get calcium sulfide, which is a salt. Calcium and sulfur are both elements with zero charge. Calcium sulfide, the calcium is +2, the sulfide has a 2- charge. Again, reactions with elements on one side, here on the left, and compounds of the elements on the other, the right side, must involve a charge of change, a movement of electrons. That means all syntheses of compounds from the elements continue to be oxidation-reduction reactions.